Welcome to Lecture 17 of our series on Prosody. Here we cover computational features that correspond directly to things that you can see and hear. This goes beyond the frame-level features discussed in previous lectures. Any one measurement can never tell you very much. Even if normalized, in order to model things that humans can truly hear, you need some context. Then you can get things like, where are the pitch peaks, how high are they, which words are louder, is there a wide pitch region here? So this lecture is about such mid-level features. These are the most relevant for speech recognition, speech synthesis, emotion recognition, speaker identification, dialogue applications, and so on. We obtain mid-level features by aggregating measurements, such as measurements at nearby times, or measurements of different prosodic features. So, aggregation, in terms of the workflow for prosody analysis back from lecture 14, is the third step. We aggregate normalized frame-level features in order to obtain mid-level features that relate to perceptions. There's lots of issues to talk about. The first issue is over what time span do you aggregate? For example, over the third word, what is the average pitch? So looking at our example again, one common strategy is to first transcribe all the words. Then you can compute, say, the average pitch over the word learning. And remembering that the F0 is in blue, you'll see that the average pitch here is relatively high. So that could be a useful feature. Or you can do this over syllables or phrases or whatever unit is appropriate. Such unit-aligned features are appropriate if you're looking at tone or stress, as discussed in lecture 10, in which the prosody is tightly linked to the units. Now there are also unaligned features. For these, we don't care about the word and syllable locations. These can include features to detect pitch excursions involving regions of wide pitch, and features to detect regions of narrow pitch. So in English, combinations of these two, in configurations like this, can convey contrast or contradiction, sort of regardless of what words they align with. So choice of alignment, if any, is a big choice we have for many features. We need to choose features to match the phenomenon. This is always true. Further, some features are intrinsically about the relations between different streams. So here we see two different streams, the pitch stream in blue, F0, and the intensity stream in green. Some features relate to both. For example, the feature that quantifies the disalignment between energy peaks, like that one, and nearby pitch peaks, like that one, is an important feature. In this case, it's barely noticeable. They align pretty well. But when large, this feature can contain things like incredulity or insinuation in English. In other languages, it can actually contain information about word identity. So if I say, talking about learning styles, you can hear a disalignment between the pitch peak and the energy peak. So in general, it's good to include multi-stream prosodic features. If you leave those out, you'll be missing some important things. Okay, let's talk about some specific features. There are many, many we could talk about. We'll just discuss a few, starting with pitch height. So pitch height seems simple. You can just average the pitch values over whatever time span you're interested in. For example, words is seen here. What could go wrong? Actually, quite a lot. So microprosody can mess things up, especially for words of one syllable. There's lots of excursions, which as we see, have no real significance, no perceptual significance. To reduce this effect, we can use features with wider time spans. After over a half a second or a second or so, microprosodic effects mostly just get washed out. Outliers are another common issue. For these, we can represent pitch in terms of percentiles. That gives us more robustness in our averages. And there are other techniques we can use listed here. Robustness is an even bigger issue for pitch range. Outliers and microprosody affect this even more. Consider the words talking and about. With the F0, the blue line here, computed using the Praat defaults, which has the wider pitch range. Well, it sounds like this. Talking about learning. Okay, did talking sound like it had a wider pitch range or about? Hard to judge. Maybe here it is again. Talking about learning. All right, well, I think you might agree that the word talking has more of a range than about here. But if you look at what Praat is telling us and naively compute the pitch range as the difference between the max and the min, it tells you a different story. The problem is, even a single wrong point, here I think we have a couple actually, in the word about, can drastically change the pitch range computation. What can we do? Standard deviation is a little bit more robust, not a lot. Really, we never actually care that much about exact pitch range in hertz or in semitones. That's not perceptually significant, as far as I know. But the difference between wide pitch range and narrow pitch range, that certainly is. And that can be more robustly computed. So, sort of a general model, backing off from things that seem mathematically exact and appropriate to things that are realistically computable and perceptually relevant can be a good strategy. Same problems arise for pitch slope, many other things. In general, functionals, like standard deviation or average, are elegant and simple, but may not be robust enough for your data. There is a school of thought which says that more features are better than that, fewer, even if some are not robust. For example, one configuration of OpenSmile had over 6,000 features. It's not that hard to get 6,000 features, actually. If you have a whole bunch of frame-level features and a whole bunch of functionals, and you might compute those over a whole number of different time spans, and you might also have processes for smoothing, normalization, pooling, you can easily get up to 6,000 features. That's a heck of a lot. It would be nice if we could just pick out the ones that are perceptually relevant, or those that just have practical value, but it turns out both are problem dependent. We'll talk more about that in future lectures. We're going to wrap up this lecture with some practical comments, first on the toolkits you might use. Many groups have produced toolkits for computing prosodic features. The overall aim is to make life easier for modelers. And if your boss tells you, we need some prosodic features, then you can use any of these and you've done what you were told. Whether or not you've obtained a set of features that are useful for any specific purpose, well, that's a different question. In that case, you'll need to dig a little bit deeper, figure out exactly what you really need, and consider all the pitfalls and issues, some of which I've talked about already. A few general comments, though, about these different toolkits. Praat, designed for linguistic research, very good for visualizing prosodic features, especially pitch, of short utterances. OpenSmile was designed for emotion detection from single utterances. The Midlevel Toolkit was designed for language modeling, for predicting the next word, given the prosodic context. And there's also Coverep and Surfboard, which are a little bit newer. All of these have been applied for many different tasks. All of these are open source. Some are customizable. Other advantages, well, there's a few listed here. OpenSmile in particular is incremental. You can apply it to a speech stream coming from a live microphone and get the features in real time. Midlevel is designed to be robust to dialogue, even with noise in the background. All right, so I'm going to end this lecture with a few comments on some less frequently used prosodic features. They can still be important. Speaking rate is very important, very hard to compute accurately. Even if you hand label all the phonemes and count the phonemes per second, that doesn't correlate superbly well with human perceptions of speaking rate. Capstral flux, which roughly measures how quickly the tongue and articulators are changing position as you speak, that is even less reliable, but it fortunately can be computed for unlabeled, untranscribed speech. Articulatory precision, whether the speaker is producing enunciated or reduced speech, you can compute that by looking at the spectral values and computing the spectral values at each time and seeing how far they deviate from the global mean, sort of the global schwa sound. Creaky voice, roughly jitter in pitch, peak alignment, time difference, unvoiced intensity ratio is an interesting one. So unvoiced consonants are usually much quieter than the vowels and voiced consonants. But if people are a little bit angry, the volume on the consonants tends to increase, and so this ratio goes down. There's many more we could talk about. All right, but we'll wrap it up here. In the next lecture, we'll illustrate how the different feature types can be used, in particular used for speech recognition. That's the task of mapping from a speech signal into the sequence of words.